The biggest shift in this week's AI research is not a new model, but a new fight over optimization geometry. Muon-style updates are becoming a practical systems primitive, cutting diffusion transformer training time in half and improving robustness in experiments connected to the optimizer used in systems like DeepSeek. Yet compress those updates to 1 bit, and the theory can fail spectacularly, even on simple objectives. These results expose the trade-offs shaping faster, more generalizable, and cheaper training, and why the strongest heuristic may still lack a guarantee. Let's explore the first paper. See Muon accelerating and stabilizing diffusion transformer training via chunked momentum orthogonalization. Researchers Chuyan Chen, Peng Sun, and Kun Yuan from Peking University, Westlake University, and Zhejiang University introduced Muon, an optimizer designed to fix Muon's late-stage convergence plateau when training diffusion transformers. Standard DIT implementations fuse functionally separate weights in eta-ln modulation, attention QKV projections, and FFN gate-up layers. Applying Newton-Schulz momentum orthogonalization to each fused matrix creates unwanted cross-subspace coupling and distorts update directions. Muon reverses this fusion logically by splitting selected matrices into independent chunks, orthogonalizing each chunk separately, and preserving the overall update norm with moonlight scaling. On ImageNet 1000 at 256 times 256, a 675 million parameter DiT-XL using VAVAE reaches FID 1.18 after 200 epochs, compared with AtomW's FID 1.21 after 400 epochs, delivering a 2x training speedup without auxiliary methods such as REPA. On the 130 million DiT-B ablation, jointly chunking FFN, QKV, and eta-ln lowers FID from 3.31 to 3.02 at 200 epochs. System optimizations, including batched Newton-Schulz kernels and overlapped communication, raise Muon throughput to 9.07 iterations per second for DTB on 8 H100 GPUs, close to Atom's 9.51, while adding negligible algorithmic overhead. Let's explore the second paper, Sharpness-Aware Minimization and Muon Robustness under the Spectral Norm. This University of Bath study examines whether sharpness-aware minimization should measure parameter perturbations with matrix-aware spectral geometry rather than a flattened Euclidean norm. The authors introduce SpecSam, which applies independent, layer-wise spectral norm perturbations to weight matrices, approximating orthogonalization with Newton-Schulz iterations, and pairs this inner step with either AtomW, SGDW, or Muon, the momentum plus orthogonalization optimizer, increasingly used in frontier language model systems such as DeepSeek. On ImageNet 1000, SpecSam Muon achieves the strongest validation results for both VYT small 16 and ResNet 50, 80.23. Top 1 accuracy for the transformer, a 5.28% improvement over the non-SAM Muon baseline at 74.95, and 78.55 for ResNet 50, a 1.50 point gain over Muon at 77.05. The same method reaches 42.18 accuracy on the out-of-distribution ImageNet R benchmark, although the 3C differences there are not statistically resolvable. The central finding is an interaction between inner and outer geometry. Euclidean SAM adds roughly similar gains to different optimizers, while spectral perturbations selectively amplify Muon. A ResNet 50 ablation shows that layer-wise budgeting alone is insufficient. Replacing spectral norms with Frobenius norms removes the Muon advantage. CFAR 100 diagnostics further indicate that Muon preserves higher effective weight and feature ranks across perturbation radii, potentially retaining representational capacity under stronger regularization. The evidence remains limited to image classification, 3-seed main experiments, and methods that require 2 backward passes plus Newton-Schulz overhead. Let's explore the third paper, Sign Compression for Muon-Sign Muon, Muon-Sign, and the Limits of Error Feedback. Maria Smirnova and Alexey Kravatsky of Miria examine whether Muon's matrix-aware spectral geometry can survive extreme sign compression at 1 bit per parameter. They compare sign Muon, which signs after Muon's linear minimization oracle, Muon U sign, which signs before it, and Muon sign, which signs on both sides. The central theoretical result is negative. All three can turn a descent step into ascent on linear objectives, with explicit counterexamples in 4x4 for sign Muon and 5x5 for Muon U sign and Muon sign, regardless of step size or momentum. Error feedback applied to the Muon output also fails in general, while EF21 Muon U sign and bidirectional EF21 Muon sign restore the standard OT -1, 2 non-convex convergence rate by compressing gradients or residuals instead. Experiments reveal a sharp theory-practice gap. On centralized CFAR10 with ResNet 18, Muon reached 94.60% test accuracy versus 94.35% for full precision Muon and 93.37% for Sign SGD. On federated CFAR10 with 11 clients, it achieved 85.72%, while the 3 sign placements differed by 2.8 accuracy points. In the NanoGPT speedrun, trained on 611 million fine web tokens across 8 NVIDIA H100 GPUs, Muon and EF21 Muon came within 0.01 validation loss points of Muon. The authors conclude that sign after the LMO is the strongest practical heuristic despite lacking a general guarantee, whereas the provably convergent alternatives pay an empirical performance cost. That's a wrap on today's AI paper highlights. Thanks for watching.